Hello friends, welcome back to Synapsara. What if I told you that computers can evolve solutions to problems just like nature evolves species? Today, we're diving into genetic algorithms, one of the most elegant optimization techniques inspired by Darwin's theory of evolution. By the end of this video, you'll understand exactly how genetic algorithms work, see them in action, and know when to use them. Let's get started. But what exactly is a genetic algorithm? Genetic algorithms, or GAs, are optimization methods inspired by the natural selection. They evolve a population of candidate solutions using selection, crossover, and mutation. But before we see evolution in action, let's understand the maths. Genetic algorithms work with three key concepts. First, fitness. Every candidate solution gets a score. How good is it? Higher fitness means better solution. Simple as that. Second, selection probability. This formula determines who gets to reproduce. It's proportional to fitness. The fitter you are, the more likely you're chosen as a parent. This creates selection pressure, just like in nature. Third, the goal. Maximize fitness over generations through evolution. Now let's see how this actually works. Here's our problem. Maximize the number of 1 second in a 6-bit binary string. The perfect solution is all 1 second. Step 1. Initialization. So let's start with a random population of 6 individuals having diverse binary strings. See these fitness scores? Individual 6 has 5, 1 second, currently our best. But individual 2 only has 2 1 second. This diversity is crucial. It gives evolution something to work with. Now, the question is, can we improve this population? This brings us to step 2, selection. We choose individuals probabilistically based on fitness because fitter individuals have higher chance of being selected as parents. Watch the yellow probability bars next to each string. They're taller for fitter individuals. That's the selection formula in action. We're running a genetic lottery where fitness buys you more tickets. We selected 2 parents using roulette wheel selection. Notice both have decent fitness. Not the worst, not necessarily the best. This balance between exploitation and exploration is key. We favor the fit, but we don't ignore everyone else. These 2 will now create offspring. This brings us to step 3, crossover, genetic recombination. Here's where the magic happens. We take our 2 parents and perform single-point crossover. Think of it like cutting 2 ropes and swapping the ends. We pick a random split point, position 3 inches this case. Everything before stays, everything after swaps. Parent 1's head with parent 2's tail creates offspring 1. Parent 2's head with parent 1's tail creates offspring 2. Look at that! We've created 2 new individuals by combining genetic material from successful parents. This is how GAs explore new solutions. Not random guessing, but intelligent mixing of known good patterns. But we're not done yet. This brings us to step 4, mutation. Crossover combines existing genes, but mutation creates entirely new genetic material. We randomly flip bits with a small probability, about 15%. Watch this bit change from 0 to 1. This might seem chaotic, but it's essential. Without mutation, we could get stuck. Imagine if all our individuals converge to the same local optimum. Mutation keeps doors open, explores uncharted territory. The mutation rate is carefully tuned too high, and we're just random searching too low and we stagnate. It's a delicate balance. Now these mutated offspring replace the worst individuals in our population, and we repeat this cycle. Alright, now for the exciting part, let's watch evolution happen in real time with a full-scale simulation. Here's our setup. We're starting with a population of 500 random binary strings. Each 20 bits is long. Our goal? Evolve them to maximize the number of ones. The perfect solution, all ones, gives us a fitness of 20. We'll run this for 200 generations and see how natural selection transforms randomness into optimization. Now, this visualization has 3 key components, and each tells us something crucial about how genetic algorithms work. First, the top panel, fitness evolution over generations. This is the heart of the algorithm. You're looking at 3 lines here. The magenta line tracks our best individual each generation, the champion of the population. This shows us the upper bound of what we've discovered so far. The green line is the population average. This is critical because it tells us whether good genes are spreading throughout the entire population or if only a few elites are doing well. Watch how it chases the magenta line, that's genetic material diffusing through crossover. The yellow line shows the worst individual still surviving in the population. Even our weakest members improve over time because they inherit genes from fitter parents. The gap between these lines, that's the fitness variance. Early on, it's wide, lots of diversity, lots of experimentation. As we evolve, it narrows as the population converges. Second, bottom left, population diversity over generations. This plot answers a critical question. Are we losing genetic diversity? Diversity measures how many unique individuals exist in our population, shown as a percentage. We start at 100%, everyone's different. As evolution progresses, this drops. Now, here's the nuanced part. Diversity loss is not bad if it's controlled. We want to converge toward good solutions. The danger is premature convergence when diversity collapses too fast and we get stuck in a local optimum before finding the global best. Watch how the curve slopes. A gradual decline, healthy evolution. A sudden cliff? That would indicate trouble, but you won't see that here because our mutation rate keeps exploration alive. Third, bottom right, the statistics panel. This is your dashboard, giving you real-time metrics. Generation counter, where we are in the evolutionary timeline. Best fitness, the highest score we've ever achieved. Average fitness, population-wide performance. This is what really matters for robustness. Worst fitness, even our stragglers are improving. Standard deviation, how spread out the fitness values are. High STOT-DEV means lots of variation. Low means convergence. Diversity percentage, same as the plot but in exact numbers. These numbers tell the story numerically while the graphs tell it visually. What should you watch for as the simulation runs? In the early generations, 0 to 50, you'll see explosive improvement. Why? Because there's so much low-hanging fruit, random bad solutions get replaced by anything even slightly better. The magenta line shoots up quickly. In the middle phase, 50 to 120, progress slows but doesn't stop. We're now fine-tuning. The average fitness catches up to the best as elite genes spread. Diversity gently declines. This is the algorithm balancing exploitation, refining, good solutions, with exploration, trying new combinations. In the late phase, 120 to 200, we approach convergence. The three fitness lines cluster together, everyone's getting close to optimal. Diversity is low but not zero, thanks to mutation keeping some variation alive. We're squeezing out the last few percentage points of performance. By the end, you'll see fitness go from around 10 or 11 out of 20 random chance to 18, 19, maybe even 20 near perfection. And remember, we didn't test all 1 million possible combinations. We intelligently searched using selection pressure, genetic recombination, and controlled mutation. That's evolution. That's optimization. That's a genetic algorithm at work. Now, let's look inside the population with a heat map. Each horizontal row is one individual, all 500 of them stacked vertically. Each column is a generation moving left to right. The color tells you fitness. Dark purple and blue means low fitness. Bright yellow and white means high fitness. Watch what happens. Generation 0, it's a mess. Dark blues everywhere mixed with some random yellows. The population is all over the map. But as we progress, notice the entire heat map shifts from cool to warm colors. By generation 100, almost everyone is yellow or white. The whole population is lighting up. This is the key insight. Genetic algorithms don't just find one good solution. They elevate the entire population. Good genes spread like wildfire through crossover. Even individuals who started terrible inherit elite genetic material and improve dramatically. By the end, it's almost completely bright, a sea of high-performing solutions. That's collective evolution in action. Let's dig deeper into two critical metrics, diversity and convergence. Top panel shows population diversity in blue and fitness standard deviation in red, both plotted against generations. The blue diversity curve starts at 100%, every individual is unique. As evolution progresses, it drops steadily. We're losing uniqueness, but that's intentional. We want the population to agree on good solutions. The key is it drops gradually, not catastrophically. This controlled descent means we're converging without getting trapped. The red standard deviation curve tells a parallel story. High standard deviation early on means fitness values are all over the place, some great, some terrible. As it shrinks, the population is clustering around similar fitness levels. Everyone's becoming elite. Bottom panel is the convergence gap, the normalized difference between the best and average fitness. When this gap is large, only a few individuals are performing well. When it's small, everyone's caught up. See that dashed line at 10%? That's our convergence threshold. Once we cross below it, the population has largely unified. What we need is the curve to go below 10% line. Now let's watch the fitness distribution evolve. This is a statistical view of the population. The x-axis shows fitness values from 0 to 20. The y-axis counts how many individuals have each fitness score. Generation 0. Look at that spread. It's almost a bell curve centered around 10 pure randomness. Some individuals have 5 ones, some have 15, most are in the middle. This is what chance looks like. As generations pass, watch the entire distribution shift right. The bars move toward higher fitness. What started as a symmetric spread becomes increasingly skewed. By generation 100 to 150, the distribution is bunched up at 18, 19, 20. Almost no one is below 15 anymore. The bell curve didn't just shift, it collapsed toward optimality. This is evolution in statistical form, transforming a random distribution into a concentrated spike of high performers, from scattered mediocrity to focused excellence. One important note, we ran this for 200 generations, and we achieved fitness scores of 18 to 19 out of 20. Excellent, but not perfect. If we extended this to 500 or 1000 generations, with our mutation rate keeping exploration alive, we'd likely see even more individuals hitting that perfect score of 20. Genetic algorithms are patient optimizers. Given enough time and the right balance of selection, pressure, and mutation, they'll find those needle in haystack solutions. The question isn't if they'll converge, it's how fast. And that's genetic algorithms' evolution-inspired optimization that transforms random chaos into intelligent solutions. If you found this helpful, hit that like button, share it with someone learning algorithms, and subscribe so you don't miss what's coming next. Because in the next video, we're diving into gradient descent, the optimization powerhouse behind machine learning and neural networks, where genetic algorithms explore like evolution. Two completely different approaches to the same goal, finding optimal solutions. See you in the next one. Keep optimizing.